Hello, students. Last classes we have seen in Unit 1, they have dealt with black body radiation, they have dealt with photoelectric effect, Compton effect, and the different atomic models, that is, Rutherford nuclear model, Bohr model, Sommerfeld model, how the experiments have supported them and the models have changed, covering each other's drawbacks. In the second unit, we will deal with de Broglie waves, the Schrodinger wave equation, how it supports the uh, status, the state of wave nature, and the experiments concerned. First of all, whatever we have studied has in unit 1 has been extended here, the wave particle duality. Now it is a concept of quantum mechanics, that is where the quantum mechanics starts. It speaks about the quantum of energy, that is light contains photons which have energy E is equal to h nu, that is called one quantum, and where every entity in nature is assigned particle as well as wave nature, because in we have first of all we have seen light electromagnetic radiation where photon was there, and that photon is a particle. So particle nature of light we have seen, which is supported by photoelectric effect, Compton effect, black body radiation, etc. The wave nature, we have seen it is supported by interference, diffraction, polarization, things like that. So one thing we must remember, that it is the effect of matter or wave that speaks about it. We have we cannot see them physically, like you are seeing a person, he is so much tall, so much broad, this that. So you must understand that we have the resolution of the instruments actually increases with using the same light which we are going to analyze. So, the same light particle cannot analyze another light particle. In the electron microscope, it uses at the most electrons. So, when the electron reaches that particle which is smaller than it, it has already vanished or finished. So, it is the effects of this radiation or matter, small particles, which speaks about themselves. And remember, it was the starting of the 19th century. So, up till then, the interference, diffraction, polarization supporting the wave nature of light, and the black body radiation, photoelectric effect, and the Compton effect, etc. Here I have written already that is supporting the particle nature of light. Similarly, we have known electron as a particle with a negative charge, very small mass, but it has some mass greater than photon. So the electron having wave nature, David Germer experiment and G.P. Thomson experiment has provided enough evidence to say that the electron beam, when many electrons are released at same time by the cathode, it forms a beam actually. So that beam, electron beam, behaves like a wave in these experiments. We will see later in an analyzed form. Now, these are the things which have backed the Planck's hypothesis, which speaks about basically about the quantum mechanics, and they have supported wave particle duality, which later on led to new ideas like uncertainty principle and quantum statistics. So, that is the importance of this wave particle duality. Now, next we should see, compare waves and particles. Basically, what are waves and what are particles? The basic difference we see is waves, they are not localized, they don't stay at a place. The definition of the wave itself is energy in transit. So when it is transferred from mechanical energy or electromagnetic energy transferred from one point to another in a periodic way, then it forms a wave. So it is delocalized. But the particle, it occupies a well defined position, as you all know. In general mechanics, you have read. Waves can interfere with each other. Interference, you have read. Particles, they don't interfere with each other. They maintain their identity even in a group. You mix a wave and wave, a new thing is formed. Okay, so it cannot be counted. So when two or more waves mix, they will form a new wave. Of course, the energy is conserved. There is no change in the total energy, but you cannot separate out that this is the energy of this wave. This you can't see them separately. Whereas particles in a group, they can be counted and they maintain their identity. When two or more waves are present in the same region, resultant wave will be larger or smaller compared to the individual waves. It will not be the same. Again, the identity question. Two or more particles present in the same region sum up. Sum of particles equal to number of individual sums. Number of particles, say m1 plus m2 is equal to total mass, like that. Now here we have given a problem for you to understand actually what we have read. Here is a body of 0.55 grams moving with velocity. See, 10 to the power 5. 10 to the power 8 means light velocity. So it is moving with this fast velocity, then it is nearing the wave nature. So the de Broglie lambda is considerably measurable. So he is asking what is lambda associated with it. So lambda equal to h by mv is the formula, h by p. So we have calculated here. Taking here, this is in CGS system, so 10 to the power minus 3 multiplied. This is in MK system only, so put like, no, meters per second, yes. It is put like that only. Why this 10 to the power minus 2 comes here? 3.5 into 10 to the power 5. See, this is H value in MK system, and this is mass, and I think this is here centimeter per second, so it is meter, it converted into meter, that's it, and there is the answer. So many meters, still it is very small, you see. 1 angstrom means 10 to the power minus 10, that is the radius of the atom. So still, now here we have, they are called wave particles associated with waves. The waves are named as, after the scientist, it is named as de Broglie matter waves. The ideas promoted by de Broglie scientist proposed concept of matter waves. So how did de Broglie visualize it? First of all, he put his argument that nature is symmetrical and radiation is exhibiting wave nature as well as particle nature, supported by interference, diffraction, polarization, black body radiation, photoelectric effect, Compton effect for particle nature, like that. Now second, nature is symmetrical, so if waves are particle like, then matter must also be wave like. That is what he proposed. Hence matter must also have dual nature. And to understand the behavior completely, certain wave aspects should be attributed to material particles. For example, we take very small particles, because big particles, they have very small wavelength, so small that they are immeasurable sometimes, and so large that they are meaningless. So here you take an electron particle which is very near to something like a photon, so it is charged, no doubt. Electron present in stable orbits should be attributed with wave nature or characteristics. While finding the path of electron, they should be treated as waves. They are revolving in an orbit, but it should be actually equivalent to a wave of wavelength lambda which is propagating in that region. So here uh, these calculations actually show how we can assign a wavelength and what may be the possible values. Here de Broglie wavelength lambda of neutron is asking to calculate, okay, and given Planck's constant and Boltzmann constant also, and he is saying at a temperature of 400 degrees Kelvin. So when temperature is mentioned, then the energy will be kT. E is equal to kT, and it is the root of 3 m kT, 2 m kT. It should be 2 actually. Okay, it's 2 by 3 actually, 2 by 3 kT something, then it comes. So here h by root of 2me formula, and check out the formula once. So this is what we have got, and 1.26 angstroms we have got for electron. Okay, here another example, find de Broglie lambda for electron moving with velocity 3 by 5th of velocity of light. Its rest mass given. So when an electron is moving with some velocity, the formula will be h by mv, but m should be the relativistic mass. When a body is moving relatively close to a velocity of light, then its mass increases and it becomes mg rho, that is rest mass, divided by root of 1 minus v square by c square into velocity. So this is taken up, this denominator taken up here, and here numerator you have multiplied by c and multiplied by c here also, here numerator and denominator c. So now if you put the values, v is equal 3 by 5 c if you put, then it will become 3 by 5 square here. This is the value of h, and here it will become v by c will become 3 by 5, and here m0 and the velocity of light. All these things together, you will get lambda 0.032 angstroms. Remember, 1 angstrom is 10 to the power minus 10 meter. So that is how it is calculated. Next is just a question how it is asked in the exam. What are matter waves? Explain their properties. Now in 1923, de Broglie proposed this matter waves, that electrons and things, small particles like that, or every particle for that sake, exhibits wave nature. So what are the properties of matter waves? Are they different from the actual waves, light waves? We have seen things like that. Now you have read about waves, they are mechanical in nature, electrical in nature, okay, and heat waves also you have seen. Some are visible, some are invisible. If you go to the electromagnetic radiation proper spectrum, you will see all those. Again, you go through in internet, you type and go through. So here we are dealing with matter waves. So m mass, supposing particle is there, it is associated with a wave which has a wavelength lambda and frequency nu. Now what are the properties? The matter waves are not physical phenomena, because the resolution of our eyes is not enough and instruments is not enough to see the waves, because they have either very high wavelength or very low wavelength. We cannot visualize them. It's not a physical phenomenon. They are pilot waves. Pilot means in the sense they are guiding. They are guiding the whole particle, and they are called probability waves also, because wherever there is an abundance of the wave shown, or it actually the particle is assigned by a group of waves, it's called a wave packet. If you go in depth, then all these waves, they will interfere constructively at some place, destructively at some place. Wherever they interfere constructively, then there will be a wave imagined or felt there. That is, the particle is there, the vibrations they call, no? Yes. So that is how it is. So they tell us if a wave is present, then we say that there is a high probability that the particle is existing there. So they are called probability waves. They are not electromagnetic in nature, and their velocity of matter waves depends on velocity of particle, as you will see later on. Group velocity, phase velocity. Group velocity is velocity of particle. So smaller the velocity of particle, greater the lambda associated with it. See, lambda is equal to h by mv. V is small, then lambda is high, and m is small, that is lighter the particle, then greater is lambda. So lambda will be great if m is small or v is small. So m small means particles like electrons, protons, intra-atomic particles. The big masses, they will produce lambda very less, and a small slow velocity. Velocity slow means compared to velocity of light, 3 into 10 to the power 8 meter per second. Not your usual walking velocity or running velocity, they are nowhere near. So here, the lighter the particle, lambda associated will be high, and usually our particles are heavy, so lambda is very less, and smaller the velocity also, lambda associated with it is very high. So our velocity is no doubt small, but our mass is equally big actually, so that the effect of the mass shows on decreasing the lambda. Now it differs from case to case anyway. The phase velocity of matter waves is called Vp, and Vp is phase velocity of matter waves is greater than velocity of light. Now I will show you in detailed explanation of this aspect. What is phase velocity actually, and how it is greater than velocity of light. So that was the point where Schrodinger, he thought of, or he visualized, that a particle cannot be represented by a single wave but a group of waves pushing forward with a velocity higher than the velocity of the particle, but they will interfere, and constructively or destructively, depending on whether the particle is there or not. The particle is there, constructive interference; not there, destructive interference. And the group velocity will be equal to the particle velocity. So we will read it later. So these are the general properties of matter waves. Now, how is this dual nature of matter or matter waves supported by Davis and Germer experiment in 1927? Davis and Germer, he took an electron beam which is being produced from a filament. Filament means a metal wire which is actually low tension battery attached to it. Then it gets heated. When current passes, it gets heated, and that heat energy given to the outermost electrons. Metals are generally high atomic number, outermost electron loosely bound. That is the theory of vacuum tubes, no? So loosely bound, it gives off easily and comes out of the atom. And when it comes out of the atom, here there is an anode like thing, cylinder like thing with a small hole, which is given a positive potential, high tension battery, thousands of volts. So this is positive compared to this. So the electrons will be attracted and they will be channelized and released in a straight line falling on a target. This is a nickel crystal, and they get reflected, and an electron collector is here. This is the electron collector, and if you rotate this target, then different angles they will be targeted. They are sent to a galvanometer, and this galvanometer tells us what the effects are here. Okay, so that is the experimental arrangement. Now this experiment is carried in vacuum, because when electrons are released, if there are gaseous atoms here, they will absorb it. So they are completely removed. This is a vacuum tube like. Then it contains three parts. One is the electron gun, second is the target, and third is the circular scale or electron receiver. Now this experiment gives first experimental evidence that beams of material particles show wave-like properties. So what are the wave-like properties? Actually, we have read is interference, diffraction, radiation, etc. Interference, diffraction, polarization. Here, the wavelength of electron beam is calculated and compared with de Broglie wavelength. De Broglie gave a particular formula: lambda is equal to h by mv. Later on we will see when an electron beam is actually accelerated. See here, there is a potential difference between these two v. This potential difference, what does it mean? Potential difference is work done on unit charge to get it through 1 volt potential. So v volts means V joules is spent on unit charge. So for E electrons, it will be E into V. Work done on electron is E into V, which is the energy of the electron, kinetic energy of the electron. So instead of the formula takes like h by root of 2 me, m is mass of electron, 2 me. So E means their energy. So energy will be small e into capital V, that is potential. So we will see the calculations, I'll repeat them. So here they are compared to de Broglie wavelength of electron, which is calculated by the formula lambda divided by root of 2me or 2m into E into V. Now, what is the experiment actually? An intense beam of electron produced from electron gun accelerated through high tension battery to the required velocity. Yeah. Okay, required velocity passing through cylinder C and made incident on the nickel crystal, which is rotated so that electron beam is reflected on all sides and falls on the electron collector. The circular arrangement consists of electron collector and a galvanometer which measures the intensity of electrons collected. Now, how do we assign a wavelength to it? Wavelength associated with electron. High tension battery is a 54 volt. And what you get on the screen is a first order diffraction maximum. On that circular screen, we get a first order diffraction maximum. What do you mean by first order diffraction maximum? Here, suppose I will just tell you the Bragg's formula because it is used here. You need not write in the exam all this, but this explanation is needed. Now here, supposing you have a crystal, and crystal is not shown here, only the dots represent the atoms of the crystal. Crystal means a regular arrangement of atoms, so they have been regularly placed. Now supposing there is a wavefront, that means light incident at an angle, say theta, not this angle with the normal, with the plane of the crystal, okay, this theta, then it is also reflected with an angle theta. Now whenever a light ray passes between the atoms, it is not reflected, okay, but at the atom when it strikes, then part of the energy received and given out, and another ray also another atom, and if these two are synchronized, I mean in many ways they have the same phase velocity, they have the same wavelength, and they interfere constructively, things like that, so they will form a coherent beam and they will produce another wavefront, and the diffraction pattern is produced. Here I have a reflected wave, but in all such reflected waves they will combine together and produce images. So the nearest image, first image to the center, to the normal, is called first order. Second image, third image, the image will be, remember, of the slit from which they have come. Slit means here the atom, the interatomic distance, that is d here, okay. So they will form an image of that slit from which they are coming. So it is, here I have written constructive interference of waves. See, there are many waves that are, but they don't interfere, only few of them from this atom and consecutive atom and from consecutive atom, like that. So constructive interference of waves scattered from atoms of a crystal occurs only when this condition is satisfied. Why this condition? See, because this wave is coming and this wave is coming. Both are traveling up till here same distance. From here also both are traveling same distance. But the second wave is traveling extra distance 2d sine theta. This is the path difference between these two waves. Path difference between these two waves. Okay, 2d sine theta. Okay, this is equal to n lambda. So, integral multiple of lambda. If the path difference is an integral multiple of lambda, then only the wave will be reflected correctly and visible, the effect will be visible. So that is what the path difference must be an integral multiple of lambda for the reflected wave to interfere constructively and produce image. So image production is done only for those waves. So that condition we are seeing. Here also I have written, see, de Broglie wavelength lambda equal to h by p, h by root of 2me. Energy is half mv square, that is p square by 2m. So p can be written as root of 2me. So if energy due to, if the electron is traveling in a high voltage region, its energy is due to the potential difference V, then energy equal to small electron charge into potential difference. So P is equal to root of 2m EV. So we have lambda formula and it is calculated. Rest are all constants. So it is given 12.27 divided by root of V. Wherever V changes, you put the value of V and calculate lambda. So this formula. So this is the arrangement which speaks of Bragg's 2d sine theta is equal to n lambda. So what we have done there, this is the actual crystal, nickel crystal, which we have used the target. And this is the electron beam which is coming. And this is produced on the circular scale. So first order diffraction is produced. Then what is theta here? This is the angle theta. This is the angle theta. And this is the angle of between the incident and reflected ray. Then 2 pi, this is total angle is 2 pi. So 2 theta, theta plus this angle, okay, equal to how much? So supposing we have the incident ray and reflected ray 50 degrees angle in this experiment, then 180 minus 50, 2 theta is nothing but 180 minus 50, so theta equal to 65 degrees. Now interplanar distance for nickel crystal is 2.15 angstroms. So 2d sine theta n lambda will give you lambda equal to 1.65 into 10 to the power minus 10 meters or 1.65 angstroms. Now similarly calculating for potential difference of 54 volts, say de Broglie wavelength, if you calculate, that also comes to be 1.67 angstroms. So these two are similar, means de Broglie said electron is associated with a wave of wavelength 1.67 angstroms. Then Davison and Germer experiment says the wavelength of the particular electron calculated is this much. So experimentally these are same, they are verified, both lambda being same. Nature of matter is experimentally verified. That matter is dual in nature, particle nature and wave nature. Here wave nature is shown. This is 4 and this is 4. Now another experiment supporting your dual nature of matter was G.P. Thomson's experiment of electron diffraction. Here he also got similar diffraction effect and something similar here. Actually this is the vacuum tube in which this is a filament producing the cathode rays and channelized by this and passing through B, so that they fall on a photographic plate here and produce a pattern like this, diffraction pattern. So diffraction pattern, fringes are obtained. So center is dark fringe and then later on fringes will obtain. So here we have seen this A part here. Where is A here? Not shown. Okay, this is the A point, then this is the B, this one. From here this figure has been shown and this photographic plate is this one, P. Okay, so here from B they will start pouring on the photographic plate through this, and this is the photographic plate. This is the photographic plate. You will have diffraction pattern like this. Supposing from here to here, this is angle theta and this is angle r, and this distance is L. This distance is L. Distance between the photographic plate and the this one here. Here, this one. This is the gun through which it is going. From there, diffraction starts. So let us see what he has done here. High speed electrons accelerated by potential difference. Same thing. So high potential difference is needed for accelerating them to a certain velocity. These electrons produced by a cathode F pass through a fine hole B and fall on an extremely thin gold metal, again a metal gold plate. Okay, film G of gold, which acts as a transmission grating. Now this is acting as a transmission grating. Transmission grating, this is the transmission grating. I will tell you what a transmission grating is. In grating experiments, we have seen that here there is a, where is the place? I forgot to, yeah. Transmission grating is something like this. It is a glass piece, and this plain glass piece, which is completely transparent, lines are drawn on the glass piece like this. Using a diamond cutter, they totally don't cut, but when lines are drawn like that, what happens is the portion on which the line is drawn, it becomes opaque. Okay, around 1500 lines per centimeter. That is what is grating. Okay, so that is what is the grating. So each between the lines it is transparent, and at the line it is opaque. So these are all windows, so many windows open. So from each window there will be a light coming out. So many rays coming out and falling on the photographic plate, then they will produce this diffraction effect. Now there it was nickel crystal, here it is gold foil. This is the gold foil, and it acts like a grating because the atoms are uniformly distributed. At the atom it is stuck, and between the atoms it passes. So when it passes, then it acts like a grating and produces the diffraction effect. So that is what is written here, photographic plate. Electron after passing through the metal foil is scattered and produces a diffraction pattern.